Come on, my dears. Today we begin with new chapter, chapter number 4. The title is Magnetic Effects of Electric Current. My dears, electric current has its electrical effect, its a heating effect, its a chemical effect also. But in this chapter we will discuss about magnetic effects of electric current. Okay, fine. The entire chapter we will discuss in 5 different sections, in which first section A we have allotted for only theories. Okay. Let us start the chapter from the preface itself with question number 1. As such, nothing is being asked from the preface, but we should not take any chances. So let us cover that also. Okay. In the preface they have introduced about one branch of physics called electromagnetism. Actually speaking, in the early development of science, there were 2 branches, electricity and magnetism, which were getting developed separately. But then scientists visually, Mr. Rowland, Mr. Ampere, Mr. Maxwell, Mr. Faraday, Mr. Oersted, these all scientists, they realized that the researches made in electricity and magnetism, they were interdependent. And because they were interdependent, the scientists thought wisely that why not to merge both the branches into one another. And then after, a single branch came into existence, and that was known since then as electromagnetism. Okay, fine. So electromagnetism is a branch which is newly prepared out of combination of electricity and magnetism. Okay, fine. Now the detailed study of electromagnetism is made in one another branch of physics, which is called electrodynamics. So what is electrodynamics? Detailed study of electromagnetism is made in one branch of physics called electrodynamics. Simple? Fine. Now so far, whatever study we have made in electromagnetism, from that study, how we are benefited, let me tell you. First of all, we have come to know about the form of light. What is light actually? That we have come to know from the study of electromagnetism. Okay. Secondly, we have been successful in generation, propagation and reception of electromagnetic waves. And because of that only, today we are enjoying all the latest technology of the communication. At present, you know, any person located anywhere on the surface of entire earth can contact any other person located anywhere immediately. And such a fast, such an advanced technology we are having because of the study made in electromagnetism. Okay. So that study is very important. Got it? Fine. Now this electrodynamics is specifically very useful in 3 fields visually: plasma physics, magneto-hydrodynamics and advanced technology of communication. In which 3 fields the study of electrodynamics is very useful? First is plasma physics, second is magneto-hydrodynamics, and third is advanced technology of communication. Got it? Fine. Now we go for question number 2. It is about Mr. Oersted's observation. There was a science teacher at one of the schools at Denmark in the year 1819. That fellow was Mr. Oersted, and he had made very useful practical observation. What is that observation? I am showing you. Consider this figure at present, in which one battery, one key and one conducting wire, say copper wire, are connected. Okay. At present this key is open, so no current is flowing in this circuit. And at that time, this magnetic needle kept above this wire, parallel to the length of the wire, is remaining steady, correct, at rest. There is no deflection observed in this magnetic needle at present. Okay. My dears, magnetic needle is nothing but a very light artificial magnet which can rotate about vertical axis in the horizontal plane quite freely. Okay. And at every place it is found to be getting settled in equilibrium in specific horizontal direction. At different places, it might be getting settled in different horizontal directions, but at a given place, it is getting settled only in a specific horizontal direction. For example, at this place, if that magnetic needle is getting settled this way, suppose, then you are supposed to keep this wire just below the magnetic needle, but parallel to it like this. Okay? If this magnetic needle is getting settled in this direction, suppose, then you are supposed to keep the wire below the needle and parallel to the needle this way. Got it? If magnetic needle is getting settled this way, suppose, then you must keep the wire this way. In any case, you must keep the wire below the magnetic needle and parallel to its length. Got it? Fine. Now, in this situation, you just do one thing, you place this key and make the circuit closed. When you make the circuit closed by placing the key, naturally current will start flowing from positive to negative terminal of the battery in the outer part of the circuit. Correct? That current I have shown by symbol I. Fine. Now, as soon as this current starts flowing through this metallic wire, it so happens that this magnetic needle is getting immediately deflected by an angle 90 degree, and then after it is getting settled in a direction perpendicular to the length of the wire. Earlier, the needle was like this and the wire was like this. Correct? This is needle. And now, with the passage of current, it starts getting deflected by about 90 degree, and finally it is getting settled perpendicular to the length of the wire. Okay? Now tell me, this was the practical observation made by Mr. Oersted. Now let us try to understand why it happens so. Why? What is the reason? I am showing you. See, this magnetic needle is getting deflected, that is a fact. Now tell me, why there is a deflection in the needle? There must be some torque exerted on the needle, correct? But you know that torque is always getting produced by exertion of some force. So there must have been some force exerted on this magnetic needle, correct? But that force we have not exerted, so it is not man-made force, it is not artificial force, then it must be some natural force. But all the natural forces are produced out of their respective natural force field. So here also some new force field must have been generated, from which the natural force is exerted, which exerts some torque, and that is why some deflection is observed in the magnetic needle. That is for sure. Correct? Now, that new force field which is getting generated here, it is generated only when you pass the current. So the source of that field is this current. Okay? Fine. And later on, the properties of this new force field were examined experimentally, and the scientists realized that this is entirely a new force field which is different than gravitational field, which is different than electrical field. Now this is such a force field which affects this magnetic needle, which has some magnetic effect. That's why that new force field was known as magnetic field. So what is the name given to that field? Magnetic field. Fine. Then what is the source of that magnetic field? It is nothing but current. The way source of gravitational field is a mass, the way source of electrical field is a charge, similarly source of magnetic field is nothing but an electric current. Okay? Fine. So because source is present, naturally that force field will arise. Okay? So what is the conclusion from this experiment? What is Oersted's observation? You can just state it this way. Whenever we pass any electric current through a conducting wire, in the surrounding region there is produced some magnetic field. Okay? Magnetic field is getting produced in the region surrounding to a current carrying wire. That is for sure. Okay? This was the conclusion from Oersted's experiment. Got it? Fine. Now, my dears, let us show that magnetic field by typical symbol. Now onwards, this magnetic field will be shown by this symbol, vector capital B. It is a vector field and it will be shown now onwards by symbol vector capital B. It has got some other synonymous names also. Either you say magnetic field, or you say strength of magnetic field, or you say magnetic induction, or you may say magnetic flux density. All these physical quantities are one and same, and it is magnetic field shown by symbol vector capital B. Okay. What is the SI unit of that magnetic field? SI unit is Tesla. You must write it with the name this way, Tesla. Okay. And if you want to write it symbolically, symbol is capital T. And its other equivalent SI units are Weber upon meter square and Newton upon ampere into meter. So, which are the three SI units of magnetic field? Tesla, or Weber upon meter square, or Newton upon ampere into meter. Got it? Fine. There is one more system of units known as EMU, electromagnetic units. It is not there in our syllabus, but just for your kind knowledge, in that EMU system of units, there is a unit of magnetic field which is known as Gauss. The spelling is Gauss, its symbol is capital G. By chance, if the value of magnetic field is given to you in the numericals in Gauss, then you must convert it into Tesla. How to convert? Very simple. Remember, any value of Gauss, if you require to convert into Tesla, multiply that Gauss value by 10 raised to minus 4. Got it? Fine. So, this was the very important observation made by Mr. Oersted in the year 1819. Later on, the same observation was placed before French Academy of Science in the year 1820 on 11th September by Mr. Arago. There was another fellow, Mr. Arago. He had placed this observation for the purpose of verification among French Academy of Science in the year 1820 on 11th September. Okay. The date is specified in the textbook just to remind you about the terrorist attack on the World Trade Center in America. That attack was also made on the same date, 11th September. That is why the date is specified in the textbook. Okay, fine. As soon as Mr. Arago had informed about this observation to French Academy of Science, then after these news were published in the entire world. And at that time, there were two fellows who were making research in the same direction. They were Mr. Bio and Mr. Sauer. In the spelling of Sauer, this T is silent. Okay? These two fellows were making research in the same direction in Paris. Within a span of 2 months, they had obtained very important practical result, and it was regarding the intensity of this magnetic field. How much is the intensity of magnetic field? On which factors does it depend? That was determined experimentally by these two scientists, and that very result itself in the memory of these two scientists is known as Bio-Savart's law. Bio-Savart's law. Okay, fine. So let us see about now Bio-Savart's law. Okay. Let us begin now question number 3 about Bio-Savart's law. See, just consider a conducting wire with some arbitrary shape. Arbitrary shape. Arbitrary shape means any random shape the way you like, but it should not have many zigzags. Okay, it might be a linear shape, it might be some curved shape. Okay, it should be a smooth curve like that. So I am showing you one conducting wire with such a smooth curve. Okay, now through that conducting wire I am passing some current, and that current is suppose capital I. Okay. Now the entire length of this conducting wire is assumed to be divided into extremely small length elements, each having length suppose dl. When I am using symbol dl, you must understand limit delta L tends to 0. Correct? Now consider one such extremely small length element, which in the figure I have shown by green color. Okay? You must assume this length element very short, very small, but just to have clarity in the figure, I have shown it with rather big dimension. Got it? Now when the same length element is taken as a vector in the direction of current, we call it length element vector. Length element vector shown by symbol vector dl. And now you please multiply it by current, and then you will get the term I into vector dl, I into vector dl, correct? This very term is known as current element, current element. Here I have written current element, it is I into vector dl. Now what is the SI unit of this current element? Very simple, ampere into meter, ampere into meter, correct? Fine. Now tell me, just now we have seen in the Oersted observation that whenever there is a current passing through any conducting wire, in the surrounding region we have production of magnetic field, correct? So surrounding to this wire also we must have magnetic field. Suppose we are interested in finding out that magnetic field at this very specific point, say point P. Whichever point you are taking into consideration, it is known as point of observation, point of observation. Let it be point P, correct? How much is the magnetic field at this very point due to this current element? Let it be vector dB. See, why not vector B and why symbol vector dB? The reason is that at present we have not considered entire length of the wire, we have considered very small part of it, and that's why, because we are considering partial length of the conducting wire, that's why this magnetic field is called partial magnetic field. You must show it by this symbol vector dB, correct? When you consider partial length, you must talk about partial magnetic field, okay? Fine. Now with respect to this current element, the position vector of this very point is suppose vector r, vector r. That is, distance of point of observation from considered length element is r, which is magnitude of vector r. And in the direction of this position vector, I have selected one unit vector which is r hat, okay? Whether you speak r hat or r cap or r caret, it is one and same. I am used to with the pronunciation r hat, okay? Symbol you must write this way, r hat, got it? Angle between this length element vector and this unit vector, let it be theta, okay? Now due to this current element, how much is the partial magnetic field developed at point P? Let it be vector dB. As I said, its formula was derived experimentally by these two scientists, Mr. Bio and Mr. Sauer, and that result itself is known as Bio-Savar's law. Its mathematical expression, mathematical presentation is this. Vector dB is equal to, come on, mu 0 I upon 4 pi into vector dl cross r hat upon r square. Again, vector dB equals to mu 0 I upon 4 pi into vector dl cross r hat upon r square. Let me give you now identification of each symbol. What is mu 0? It is a physical constant called permeability of vacuum, permeability of vacuum, permeability of vacuum, okay? In the spelling of vacuum, it is VACWM. Be careful. You may not trust me, better you refer dictionary, then you will realize, okay? VACWM. This is the correct spelling for vacuum, okay? This mu 0 is called permeability of vacuum. What is its value? Its value is 4 pi into 10 raised to minus 7. Unit is Tesla meter upon ampere. Here it is. 4 pi into 10 raised to minus 7. Unit is Tesla meter upon ampere, or equivalent unit is Weber upon ampere into meter, okay? Now actually what is called permeability of vacuum, that I will explain to you in the next chapter. If you remember, regarding permittivity of vacuum, I had explained very nicely. Similarly, I will explain this term also, but in the next chapter, because whatever explanation I require before going for explanation of this, that still remains to be studied, okay? So let us study those topics first, and then after in the next chapter, I will definitely explain about permeability of vacuum in very much details, okay? Fine. Now, as such, this constant, if required in numericals, they will give you, but if at all you remember, then you will be benefited, because sometimes they may forget to give you that value, okay? Please. Now, how would you give the statement of this Bio-Savar's law from this mathematical format? Very simple. Due to a current element I vector dl, the magnetic field produced at a point of observation having position vector vector r with respect to that current element is vector dB equals to mu 0 I upon 4 pi vector dl cross r hat upon r square, full stop. This very statement is called Biot-Savart's law. I repeat, due to a current element I vector dl, comma, the magnetic field produced at a point having position vector vector r with respect to that current element is vector dB equals to mu 0 I upon 4 pi into vector dl cross r hat upon r square, full stop. This very statement is called Biot-Savart's law. Last time now, due to a current element I vector dl, comma, magnetic field produced at a point having position vector vector r with respect to that current element is vector dB equals to mu 0 I upon 4 pi into vector dl cross r hat upon r square, full stop. This very statement is called Biot-Savart's law. Correct? Fine. Now, what about direction of this magnetic field? Very simple. You can simply find out direction of this vector product, vector dl cross r hat. Let us find out using law of right-handed screw, what you have studied in 11th standard. Correct? Fine. Look, this is vector dl, correct? And this is vector r hat. I want vector dl cross r hat. Come on, consider this situation. Take this as vector dl, okay, in this direction, and take this as vector r hat. Both these vectors are right now in the plane of the figure on the surface of board, correct? Now, this is the angle between them. Let it be theta. Now, take this as first vector, take this as second vector. Now, according to law of right-handed screw, first of all, we are supposed to consider one right-handed screw perpendicular to the plane passing through these two vectors, correct? Let the screw be this one, and now I am supposed to rotate the screw in a manner first vector rotates towards second vector. First vector is vector dl, second vector is r hat. I must rotate vector dl towards r hat this way, correct? Fine. Now, if I rotate this screw this way, correct, definitely it will go inside the plane of the figure perpendicularly, correct? And in a physics, remember, there is a tradition, if any direction is going inside the plane of the figure perpendicularly, we show it by symbol of cross, okay? That's why I am putting symbol of cross, just to indicate the direction of this magnetic field perpendicularly inside the plane of the figure. Got it? Fine. Had it been outside, then you can show it by symbol of dot. When it will be perpendicularly outside, provided if you reverse the direction of current. If direction of current is getting reversed, then this current element will be taken this way, in this direction, in opposite direction, correct? Then in that case, the result will be like this. Situation will be like this. This is vector dl, this is vector r, and now this right-handed screw you can consider like this. And in that case, this first vector, this will be second vector. You are supposed to rotate first vector towards second vector this way, correct? So manner of rotation will be now this way, correct, anti-clockwise. And if you rotate this screw this way, it will be getting unscrewed, it will be getting open up, and it will come out of the plane of the figure perpendicularly. And then it should be shown by symbol of dot, correct? Going inside the plane of the figure perpendicularly, then cross, coming outside, then dot. Got it? Please remember these two symbols. Come on. What about this position vector? Don't you know from 11th standard? Vector equals to magnitude multiplied by unit vector. Come on. Vector equals to magnitude multiplied by unit vector. Correct? Find out this unit vector. It will be vector r upon r. Vector r upon r. You know, whenever you divide any vector by its magnitude, you will definitely get unit vector in the same direction. Correct? Fine. Now just write vector r upon r in place of r hat in this formula. Come on. Instead of vector r hat, I should write vector r upon r. Write it here. When you write here vector r upon r, here it will appear vector r, but divided by r, that r will be multiplied here, giving you r into r square, that is r cube. Here it is r cube. Correct? Please remember, don't get confused. If it is head, then it is square. If it is vector, then it is cube. Head then square, vector then cube. Just remember, head then square, vector then cube. Okay, fine. Now this is the partial magnetic field, which is magnetic field at point P only due to this considered single current element. But actually, if we want the resultant magnetic field at point P due to this entire current carrying wire, then what you should do, you should change the position of this current element right from this end to this end continuously along the length of this wire, and each time you are supposed to find out the values of partial magnetic field, and then after you should make their vector addition, and that vector addition you can find out mathematically by just taking line integration of vector dB along the length of this wire, correct? That is why I am going for now line integration on both the sides, correct? Line integration of vector dB, and when you take line integration here, this part is constant, so it is taken out. Mu 0 I upon 4 pi taken out, integration of vector dl cross vector r upon r cube. But now tell me, when you add vectorially all the partial magnetic fields, naturally it will give you resultant magnetic field at point P. Let it be shown by symbol vector capital B, correct? And now this part as it is, but mind well, this is the line integration, that's why I am putting L, okay, fine. Now what is the physical importance of Biot-Savart's law? Physical importance of Biot-Savart's law. Using Biot-Savart's law, you can determine the magnetic fields produced by uniform current distributions. What you can do? Using Biot-Savart's law, you can find out the magnetic fields produced by uniform current distributions. This fact gives you its physical importance. The way using Coulomb's law, you can determine electric field. Similarly, using Biot-Savart's law, you can determine magnetic field, correct? One more similarity between these two laws, they both are called inverse square laws. Inverse square laws. Inverse square laws. You know Coulomb's law, F equals to 1 upon 4 pi epsilon 0 q1 q2 upon r square. There F is inversely proportional to square of distance, correct? Here this magnetic field is inversely proportional to square of distance. Both the laws are called inverse square laws, okay, fine. Now in our syllabus, we have to study about two applications of Biot-Savart's law. One is finding magnetic field due to extremely thin straight current carrying wire, and another is finding magnetic field due to extremely thin current carrying circular ring, okay. So let us go for those two applications now one by one, okay. Now we go for question number 4 about magnetic field produced by current carrying thin straight wire. Magnetic field produced by current carrying thin straight wire, okay. And then after we will definitely go for this new concept, magnetic field line. My dears, in the textbook, they have not derived this very important result. They have assumed that result. The final result they have taken granted, okay. Simply they have written the final formula, but then all the good students, they will definitely try to understand how this formula is derived. So I am just taking you in all the necessary details, okay. I am going to derive that formula just for your mental satisfaction, not important from examination point of view. But if you try to understand, naturally it will develop your concepts. So please concentrate, please try to understand, okay. One more thing, what is more important, it is the concept of magnetic field line, which is not at all explained nicely in the textbook, and from this discussion you will really understand about magnetic field line, which is very necessary, okay. Come on now, let us begin to derive this formula. Now the situation is like this. First of all, you just consider infinitely long, extremely thin straight wire, which is at present assumed to be superposing on x axis, okay. But that infinite length you simply have to imagine, you cannot realize it in the practice, okay. So, in practice in the figure what we can show? Only limited length of that infinitely long wire. That limited length I have shown here from point C to point D with this green color. This is current carrying wire with limited length. Okay, fine. So, we consider finitely long current carrying straight thin wire. Now, current passing through this wire is suppose capital I and it is passing towards x axis, I mean positive x axis. Okay, fine. Now, on this x axis here I consider origin. Fine. Now, you know whenever current will pass through the wire in the surrounding region we will have production of magnetic field, and we want to determine that magnetic field at a specific point. Let that point of observation be point P on this y axis at distance small y from this straight wire. Okay. So, what is small y? Perpendicular distance of point of observation from this current carrying straight wire. Okay, fine. Come on. Now, you just select one current element in the direction of current. In this direction of current, I just select one current element which I have shown here, correct. The length of that current element I am showing by symbol vector dl, correct. But you know vector equals to magnitude multiplied by unit vector. Because this length is located on the x axis, we just show that magnitude by symbol dx. Okay. And you know direction of length element vector is the direction of current, which is right now positive x axis, and so unit vector will be I hat. Got it? Fine. Now, the distance of this current element from this origin is suppose x. So, distance OQ is x, correct. Distance OP is y. And now, with respect to this length element, the position vector of this point of observation is vector QP, which is shown by symbol vector small r, correct. Come on, because it is the right angle, the opposite side will be hypotenuse. Now, you can apply Pythagoras theorem, r square will be equal to x square plus y square, correct. Here it is, r square equals to x square plus y square. Just take power 3 by 2 on both the sides, correct. Now, this 2 will cancel, giving you r cube, this right hand side as it is x square plus y square whole raised to 3 by 2, correct. Now, apply method of triangle of vectors for vector addition. In this triangle, look, this is vector which is x into I hat, because vector equals to magnitude multiplied by unit vector. So, this vector is magnitude is x and direction is along x axis, so unit vector is I hat. What is this vector? It is vector r. And what is this vector? Come on, magnitude multiplied by unit vector. This much magnitude is y, unit vector along positive y axis is j hat, correct. So, vector OQ plus vector QP will be equal to vector OP. Vector OQ plus vector QP will be equal to vector OP. Come on, vector OQ plus vector QP equals to vector OP, correct. Just put the respective symbols. Vector OQ is nothing but x I hat, here it is x I hat, plus vector QP. Vector QP is nothing but vector r, and that equals to vector OP. Vector OP is y j hat, correct. Fine. Now, find out vector r from here. Transfer this, will become minus y j hat minus x I hat, correct. Y j hat minus x I hat, correct. And now, while applying Biot-Savart's law, I require this vector product vector dl cross vector r. So, let me find it out. Vector dl cross vector r, I want vector dl, it is nothing but dx into I hat, here it is dx into I hat, cross, come on, what is vector r? It is right now y j hat minus x I hat, come on, y j hat minus x I hat, correct. And now, take the cross product between these two, y dx, I hat cross j hat, it is nothing but k hat. So, I have written here k hat, correct. But then next term would be 0 vector because x dx, then it is I hat cross I hat. I hat cross I hat is nothing but 0 vector, and whenever any term is multiplied with 0 vector, that will give you 0 vector, and there is no meaning of adding or subtracting 0 vector, correct. So, I am not writing that term because it is 0 vector. Now, due to this current element, what is the partial magnetic field at this very point? Let it be vector dB, correct. The magnetic field produced by considered current element at point P is vector dB. According to Biot-Savart's law, it is mu 0 I upon 4 pi into vector dl cross vector r upon r cube. Here it is, mu 0 I upon 4 pi into vector dl cross vector r upon r cube. Earlier we had seen the same formula. Look here, vector dB equals to mu 0 I upon 4 pi into vector dl cross vector r upon r cube. Remembered, hat then square vector then cube, hat then square vector then cube, correct. Fine. Now this part as it is, okay. What is the formula for vector dl cross vector r? We have obtained. This formula is at present y dx k hat, y dx k hat, correct, divided by r cube. And what is r cube? It is x square plus y square whole raised to 3 by 2. Come on, x square plus y square whole raised to 3 by 2, correct. Now tell me, I want this values y dx and x square plus y square whole raised to 3 by 2, and for that what we do? We assume this angle to be theta. Which angle is taken as theta? Angle OPQ. Angle OPQ I just assume to be theta, okay. Then in this right angle triangle, what is tan theta? Opposite to theta divided by adjacent to theta. Opposite to theta is x, adjacent to theta is y. So, tan theta equals to, come on, x upon y, correct. Find out x, transfer this. So, x equals to y tan theta, x equals to y tan theta, okay. Now, take this y as constant and take derivative on both the sides with respect to theta. Then you may have a question, why the value of small y is to be taken constant? Because look, what is the perpendicular distance of this point of observation from this wire? It is small y, okay. Now, that perpendicular distance small y is suppose this much. This is the wire and this one is the point P, this one is perpendicular distance small y. But not necessary that point P you can take here only, you can take it here also, correct. Then also this perpendicular distance is y only, you can take it here also, you can take it here, correct. So, you just think of a circle, you just think of one circle having radius small y, okay. So, if you think a circle of radius small y around the wire taking the center point on the wire, then for all the points on that circle, their perpendicular distance from the wire would remain same, and it is y which is constant, okay. That is why this value of y I am going to take at present constant. Taking y as constant, you take derivative on both the sides with respect to theta. Look, then it will be dx by d theta here, and here y is taken constant. D by d theta of tan theta is sec square theta. Remember this formula from trigonometry, d by d theta of tan theta is sec square theta. What is that sec theta? It is a trigonometric function and it is nothing but 1 upon cos theta. 1 upon cos theta is known as sec theta, okay, and here it is square of it, so I am writing sec square theta. Got it? Find out dx now, transfer this d theta here. So, dx will be y sec square theta d theta, y sec square theta d theta, but I want y into dx, y into dx. That is why I just multiply here by y, then it will be y into dx, and when you multiply by y here, y into y will be y square, remaining part as it is. Got it? And now I want x square plus y square whole raised to 3 by 2. Let me find it out. I start with x square plus y square whole raised to 3 by 2. Now x square, can't you find it from here? X square will be y square tan square theta. Come on, x square equals to y square tan square theta, correct, plus y square as it is whole raised to 3 by 2, correct. Now this y square you can take common, inside the bracket it will be 1 plus tan square theta, and in 11th standard you had studied about 3 identities. Come on, among those 3 identities, one was 1 plus tan square theta equals to sec square theta, 1 plus tan square theta equals to sec square theta. So 1 plus tan square theta will be replaced by sec square theta, correct, and then whole raised to 3 by 2 as it is. Just take the power now. Come on, 2 will cancel, then it is y cube. When you multiply, sec square theta whole raised to 3 by 2, these two powers will get multiplied, 2 will cancel, giving you sec cube theta, correct. And now put up this value and this value in this formula. Start with this vector dB, and that equals to, come on, mu 0 I upon 4 pi into y dx k hat, but value of y dx is y square sec square theta d theta, y square sec square theta d theta, and k hat you must write, don't forget, this k hat is very important. From that term only we can find out the direction, okay, so don't miss that term, and divided by x square plus y square whole raised to 3 by 2, x square plus y square whole raised to 3 by 2 is y cube sec cube theta, here it is y cube sec cube theta, correct. Now simplify, y square divided by y cube, so there will be single y in the denominator which you can multiply here, so mu 0 I upon 4 pi y, mu 0 I upon 4 pi y, correct, and sec square theta upon sec cube theta, so it is 1 upon sec theta, 1 upon sec theta is nothing but cos theta, 1 upon sec theta is nothing but cos theta. So I am writing here cos theta d theta into k hat, got it, fine. Mind well, this is the magnetic field at point P due to only one current element, that's why we call it partial magnetic field, correct, but actually speaking we want resultant magnetic field at point P due to this entire current carrying straight wire, correct, and for that what you must do, you must consider such current elements right from one end to another end continuously, and each time you must find out such partial magnetic fields, and then after you are likely to make their vector addition, and this whole process you can carry out mathematically by taking line integration of this result over this length, okay, fine. So I am supposed to take integration of this result, and that would give you resultant magnetic field at point P due to this entire current carrying wire, okay. So let me go for now integration of vector dB, but when you take integration on right hand side, this part is constant, mu 0 I upon 4 pi y taken out, integration cos theta d theta, k hat. Now tell me, here variable is in terms of theta, so you must specify the limits also in terms of theta, but those limits you must determine in such a manner that all the current elements must be included right from one end to the another end, okay. And for that, you know what we do, we just take this angle on left side of this y axis to be negative, and on the right side of this y axis we take this angle to be positive. By showing negative value of angle, we indicate the presence of current element on the left side, correct. By showing positive sign of the angle, we indicate the presence of current element on the right side, got it, fine. Now if theta is increased right from minus theta 1 to plus theta 2, then you can include all these current elements right from this end to this end, correct. Look, say this is y axis, and this is, come on, length element PC, okay, and what is this angle, minus theta 1. So this angle is right now minus theta 1, correct. You increase it, when you increase it from minus theta 1 you can make it 0, and then after further you may increase it from 0 to plus theta 2, correct. I repeat, come on, from minus theta 1 to 0, and then after from 0 to plus theta 2, correct. I repeat, minus theta 1 to 0 and 0 to plus theta 2. then you can just go for continuous integration from minus theta 1 to plus theta 2. And when you vary the value of theta continuously from minus theta 1 to plus theta 2, you are going to include all the current elements, and then naturally you will get resultant magnetic field at this point P due to this entire current carrying straight wire. Got it? That's why the lower limit of integration is right now minus theta 1 and the upper limit of integration is plus theta 2. Got it? Vector addition of partial magnetic fields will give me resultant magnetic field. Let it be vector B. Now this part as it is. And don't you know, derivative of sin theta is cos theta. If derivative of sin theta is cos theta, then integration of cos theta will be sin theta. Integration of cos theta is sin theta. But what about the limits from minus theta 1 to plus theta 2? From minus theta 1 to plus theta 2. Okay? Don't forget this k hat. Okay? You may multiply this k hat here also, no problem. Now this mu 0 I upon 4 pi y as it is, you know how to substitute the limits. First of all, you must place the upper limit, and then after putting minus sign, you are supposed to put the lower limit. Instead of theta, I must write first of all theta 2. So I written here sin theta 2. After putting minus sign, instead of theta, I am supposed to write minus theta 1. So it is sine of minus theta 1. This k hat as it is. Got it? And there is a formula in trigonometry, sine of minus theta is minus sine theta. So sine of minus theta 1 will be minus of sine theta 1, and that minus and this minus will become plus, giving you here sine theta 1 plus sine theta 2 in bracket, outside the bracket k hat as it is, and this term also as it is. Okay. Now in textbook, this result they have written directly. I hope you have understood the entire derivation. Okay. Fine. Tell me about these two angles. Regarding theta 1 and theta 2, be very specific. What are they? I am showing you. Theta 1 and theta 2 are the magnitudes of angles made by line segments joining point of observation with the two ends of wire and the normal drawn on the wire. I repeat, theta 1 and theta 2 are the angles made by line segments joining point of observation and the two ends of wire with the normal drawn on the wire. Correct? Fine. Now, similar formula we can obtain in terms of other values of angles, and those other angles are shown here, alpha 1 and alpha 2. In terms of alpha 1, alpha 2, what would be that formula? I am showing you. Magnitude of this is theta 1, this is alpha 1. The summation of these two must be 90 degree because already this angle is 90 degree. So here I have written alpha 1 plus theta 1 is 90 degree. Similarly, alpha 2 plus theta 2 will be 90 degree. Alpha 2 plus theta 2 will be 90 degree. Correct? Find out theta 1 from here. It will be 90 degree minus alpha 1. Theta 2 is 90 degree minus alpha 2. Put them here. Theta 1 is 90 degree minus alpha 1. And sine of 90 degree minus alpha 1 is nothing but cos alpha 1. Correct? What about theta 2? It is 90 degree minus alpha 2. Sine of 90 degree minus alpha 2 is nothing but cos alpha 2. Correct? This k hat as it is. Mind well, these angles are different and the function is also different. Here it is sine, here it is cos. Okay? Now tell me, what are alpha 1 and alpha 2? Alpha 1 and alpha 2 are the angles made by line segments joining point of observation and two ends of wire with the wire itself. Okay? Angle made by this line segment with the wire is alpha 1. Angle made by this line segment with wire is alpha 2. I repeat for the last time. Alpha 1 and alpha 2 are the angles made by line segments joining point of observation and the two ends of the wire with the wire itself. Okay, fine. Now, let us consider one special case. Suppose this wire is imagined to have infinite length. Okay? If considered wire is infinitely long, then tell me, this end will just go at infinite distance. this end also will go at infinite distance. As this end moves towards left, the magnitude of this angle will go on increasing, correct? And similarly, as this end goes towards right hand side this way, then magnitude of this angle will also go on increasing. Finally, what will happen? Look, as the left end will reach at infinite distance, come on, finally this angle will become 90 degree, correct? Similarly, when this right end goes towards infinity, then this angle theta 2 will also become 90 degree, correct? So by the time both the ends reach to infinite length, infinite distance, both the angles theta 1 and theta 2 will tend to become 90 degree, correct? So if considered straight current carrying wire is of infinite length theoretically, then theoretically the values of theta 1 and theta 2 you can take 90 degree, come on. If theta 1 and theta 2 both are 90 degree, you can put them here. Sin 90 is 1, sin 90 is 1. 1 plus 1, that is 2. 2 2s are 4. So here it will now appear 2. That is why it is mu 0 I upon 2 pi y. Mu 0 I upon 2 pi y. Don't forget this k hat. Correct? And now tell me, if you take magnitude on both the sides, then magnitude of this is B. Magnitude of this is mu 0 I upon 2 pi y. Correct? Mu 0 I upon 2 pi is constant. This is the perpendicular distance from the wire that you may vary, and if you change y, definitely B value will change. But what is the relation? Relation is B is inversely proportional to y. Because B is inversely proportional to y, the equation will be B into y equals to constant. B into y equals to constant is very much like x into y equals to constant, which is equation of hyperbola. That's why graph of B versus y in this case will be hyperbola like this. Okay? As y increases, come on, value of B decreases. Got it? Fine. Now my dears, what about direction of this magnetic field? Direction of this magnetic field at point P is k hat. And what do you mean by k hat? K hat is nothing but the direction of positive z axis. How is the positive z axis? In the figure I am showing you. This is positive x axis, this is positive y axis, then positive z axis will be like this, perpendicularly outward from the plane of the figure and perpendicular to both x as well as y axis, correct? But the same direction you should consider at point P, the direction will be like this. Now tell me, this is the direction coming out of point P, coming out of the plane of the figure perpendicularly, and that's why I am putting dot here, correct? So direction of this magnetic field is perpendicularly outward from the plane of the figure, that's why I am putting dot, correct? If it is perpendicularly inside, then cross. If it is perpendicularly outside the plane of the figure, you must put dot. Got it? Fine. Now try to understand, my dear, about the concept of magnetic field line. What is that magnetic field line? I am showing you practically. Take this as radius of some circle, and that circle I am showing around the wire this way. Okay? This circle has radius, suppose y, which is considered around the wire. The center of that circle is on the wire. Okay? And suppose that circle is this, the periphery or the edge of this circular plate. Okay? Fine. Now tell me, consider point is here at the top, and at that very point in this present situation, this magnetic field came out to be in the direction of positive z axis, correct? That is perpendicularly outside the plane of the figure. So at this very point, the direction of magnetic field is like this. Look. Now tell me, at the same point, if I think of radius of this circle, then it is this radius, correct? Something like this, correct? This is radius and this is tangent. Now for a circle, tell me, what is perpendicular to radius? It must be tangent. It must be tangent. Fine. So at this very point, the direction of magnetic field comes out to be like this, in the direction of tangent, which is perpendicular to this radius at the same point, correct? Not only for this point, for every point on the circle, the direction of magnetic field is found to be along the tangent. For example, if you find out direction of magnetic field at this very point, it comes out to be like this, along negative y-axis, downwards, vertically downwards. At this very point, it is coming out along negative z-axis, that is perpendicularly inside the plane of the figure. At this very point, the direction of magnetic field comes out to be like this, that is along positive y-axis, vertically upwards, correct? So this is such a curve considered in the magnetic field such that the tangent drawn at every point on which gives me direction of magnetic field at that very point. And don't you know, according to definition, such a characteristic curve itself is known as field line. At present we are talking about magnetic field, that's why this curve will be called magnetic field line. If you remembered, in chapter number 1, we had defined electric field line this way, a characteristic curve in the electric field, the tangent drawn at every point on which gives us direction of electric field is called electric field line. Similarly, a characteristic curve considered in the magnetic field, the tangent drawn at every point on which gives me direction of magnetic field at that very point is called magnetic field line, correct? So here in the case of current carrying extremely long thin wire, the magnetic field is produced around the wire with having magnetic field lines circular, correct? In case of magnetic field produced by extremely long thin current carrying straight wire, remember the magnetic field produced around the wire has magnetic field lines in the form of concentric circles whose common center is on the wire itself. Now tell me, if you increase the perpendicular distance, what will happen? I am showing you. If you increase this perpendicular distance, means you are increasing the radius. So here I have shown some concentric circular magnetic field lines whose common center lies on the wire itself, okay? This radius I am taking as y1, look here, this radius is y2, this radius is y3. Now tell me, as distance y will increase, come on, magnetic field will decrease, magnitude of magnetic field will decrease. That's why compared to this tangent, you can see length of this tangent is less. Compared to this tangent, length of this tangent is less, okay? As distance y keeps on increasing, the strength of magnetic field goes on decreasing, correct? And each such point I am showing dot just to indicate the direction of magnetic field perpendicularly outside the plane of the figure, correct? And if it is perpendicularly inside, then you must show cross here. If you draw tangent here, it will be perpendicularly outside the plane of the figure. But what about here? It will be perpendicularly inside the plane of the figure. Perpendicularly inside, then I am putting cross, correct? Fine. So these are the circular magnetic field lines. I remind you once again, magnetic field line will not give you direction of magnetic field. No, the tangent drawn at a given point on the magnetic field line will give you direction of magnetic field. Please remember. Fine. So this is how I introduced the concept of magnetic field line, which is not explained satisfactorily in the textbook. I hope you have understood, correct? See, not necessary that every time the magnetic field will have circular magnetic field lines, not necessary. These are the shapes in the form of concentric circular magnetic field lines in case of magnetic field produced around extremely long current carrying straight wire, correct? Fine. Now, if you consider this current carrying straight wire not horizontally but vertically, then how those magnetic field lines will appear, I am showing you. Look here. Consider this vertical wire carrying current in vertically upward direction. At that time, there are circular magnetic field lines in the surrounding magnetic field, which I have shown in the diagram, okay? Here also you can see the perpendicular distance is y, and when value of y is increased, come on, corresponding magnetic field will decrease. That's why as I am increasing the distance y, the length of this tangent I am showing lesser and lesser, just to indicate the decrease in magnetic field. Come on. This distance y3 is greatest among this y1, y2 and y3. Come on, y3 is greater than y2, greater than y1. y3 greater than y2, greater than y1. And correspondingly, come on, b1 is greater than b2, greater than b3, or b3 will be less than b2, less than b1. What do you notice in the figure? As perpendicular distance from the wire increases, corresponding magnetic field decreases. y3 greater than y2, greater than y1. y3 greater than y2, greater than y1. And then b3 less than b2, less than b1. b3 less than b2, less than b1. Similarly here, this is y1, this is y2, this is y3, correct? y3 greater than y2, greater than y1, then b3 less than b2, less than b1. Got it? Fine. My dears, just now we have seen that in case of magnetic field around current carrying straight thin wire, the magnetic field lines are circular. That is true. But in which manner they will encircle the current carrying straight wire, that remains to be seen. I am showing you that also. There is a rule for that. It is called right hand rule. Now what is that right hand rule? I am showing you. Hold this current carrying straight wire in the right hand palm such that thumb should point in the direction of current. Thumb should point in the direction of current. Then in whichever manner the fingers of right hand palm take a turn around the wire, in the same manner the magnetic field lines also take turn around the wire. Correct? And when magnetic fields lines are taking turn this way, you can see they are coming out from the upper part, and because they are coming out, I am showing dots, and from the lower part they are going inside the plane of the figure, then I am putting cross symbols. Got it? Fine. And this part of the magnetic field lines which are behind the wire, I am showing by dotted curve, and this part which is in front of the wire, I am showing by the solid curves. Got it? Fine. What about in this case? Hold the current carrying straight wire in the right hand palm such that thumb should point in the direction of current. Then in whichever manner the fingers of right hand palm take a turn around the current carrying wire, in the same manner magnetic field lines also take a turn around the current carrying straight wire. Okay? And the manner of circulating is like this, and in the same manner I have shown these magnetic field lines taking a turn around this wire. Got it? Fine. Suppose you are reversing the direction of current, not vertically upwards but vertically downwards, then the magnetic field lines will take turn this way, because when you hold the wire in such a manner that thumb should point in the direction of current, then you must hold it this way with thumb pointing vertically downwards, because current is now vertically downwards. Then the fingers of right hand palm will take turn this way. At that time magnetic field lines also will take turn this way. Correct? Fine. Got it? Please.